All right, so we've got sort of one last bit about chemistry, and then you are done with 351. So the last chapter we're going to talk about is about kind of reactive species called radicals. And by radicals, we mean things that have unpaired electrons. So everything, if you've noticed, that we've done so far with reactions has been two-electron chemistry. Nucleophile attacks electrophile, HOMO attacks LUMO. Example, the SN2 reaction involves two electrons in a lone pair, for example, attacking an empty sigma star antibonding orbital. But there's a whole other area of chemistry that involves what we'll call single electron chemistry. That's just molecules with unpaired electrons. So to just introduce this, you can think about radicals, especially in organic molecules, as being electron deficient. And so in general, we're going to see that radical stability tracks with carbocation stability. The same things that stabilize carbocations will stabilize radicals. And radical structure is going to be very similar to carbocation structure. As an example, methyl radical, CH3, just like methyl carbocation, we're going to think of as sp2 hybridized and trigonal planar. And we're going to think of the radical as being in the unpaired electron is in the p orbital. It's not an empty p orbital, it's a singly occupied p orbital. When you're dealing with single electron chemistry, you drop the highest occupied and molecular orbital because it's not completely occupied. We'll call that highest occupied, singly occupied molecular orbital the SOMO, the singly occupied molecular orbital. But in general, the unpaired electron is going to be the business end of the radical. It's going to be the part of the molecule that's going to do reactions. I told you trends in radical stability mirror those or are analogous to those in carbocation stability. So a methyl radical is not as stable as primary radical, which is not as stable as a secondary radical, which is not as stable as a tertiary radical. And this will be important later on. And at some points, we're going to choose mechanisms and products that go through more stable radical intermediates in the same way that with, whoa, didn't know we could do that. That's kind of weird. How do I stop that? Anybody know?
You click on the three dots.
The three dots, thank you. Okay. No, still no. Ah, there we go. All right. Yikes. Sorry about that. Technology. Huh? Anyway, we're just like we chose with, say, alkene chemistry to go through carbocation intermediates that are more stable. We will similarly choose to go through radical intermediates that are more stable. Let's see, resonance stabilizes radicals as well. So we can take our familiar allyl carbocation system and instead add just one electron to make the allyl radical. And you can draw a resonance structure in which you put the radical on carbons 1 and 3. And in fact, if you were to draw the pi molecular orbital picture, it would be exactly the same as, say, the carbocation, only the highest orbital would be singly occupied. So your SOMO is again going to be that orbital that's only on carbons 1 and 3 and never on carbon 2. All right, so resonance stabilizes radicals. Now, a convention for dealing with radicals in drawing mechanisms is that we have to use a different kind of arrow. That is, the conventional arrow that we've used in mechanisms has been a regular arrow with two, I don't know what we'll call those things, flags, pointy things, double-headed arrow, I don't know. For a radical, because it represents only motion of a single electron, we're going to use sort of the fishhook arrow. There you go. Yeah. Okay. So, for example, to interchange between these two resonance structures, I could use arrows like this. This electron comes here, this comes here to form a new pi bond. If I want to, I can draw a third arrow to show one electron being left behind on carbon 1. But actually I don't have to. That's implied by the fact that I only used one of the fishhook arrows here. Okay? So that's one different thing about showing radical mechanisms. Now, we need to talk about where we get radicals from. And in general, to make an unpaired electron, you need to break a bond. Now, in the very beginning of the class, we talked about bond strength in terms of what we called homolytic bond breaking. And bond strengths listed in various tables in chapter 1 often showed, let's see, I don't have any numbers in front of me, but homolytic bond breaking is where, say, you take bromine and you go from the bromine molecule to two bromine radicals. The bond breaks and each partner gets an electron. And conceptually, we talked about that at the beginning of the class. You have, here is your bromine-bromine sigma bond, and you've got two electrons in it. Up here is the energy level for the unpaired bromine atoms, which each would have an electron. And the strength of the bond is the energy required to promote the electrons back up to this energy level. And so what you're doing in breaking a bond, homolytic bond breaking, is you're supplying enough energy to separate two atoms at infinite distance, but each one gets an electron and they're neutral and uncharged. So how do we supply the energy for homolytic bond breaking? Usually this is in the form of heat or light. And you'll see multiple, either of these methods are used to generate radicals. Typically, to get a radical reaction going, you need something that's called a radical initiator. And a radical initiator is something that has a pretty weak sigma bond. Usually, it's a sigma bond between two electronegative heteroatoms. And if you supply heat or light, you can get the reaction to go. Or rather, you can generate a radical. So, some examples of radical initiators. The bromine-bromine bond is weak, so you can use either heat or light. Guess I got that backwards, to generate your two bromine radicals. Peroxides of various kinds. A peroxide is a molecule that has an oxygen-oxygen sigma bond. One of these R groups, or both of them, could be a hydrogen. You could use hydrogen peroxide as a radical initiator too. You provide light of the right wavelength or heat, either one, and you can break the oxygen-oxygen bond to get your radical species. There are even more creative radical initiators. and we don't need to do a comprehensive survey of them because there's tons of them. One that's really popular in organic chemistry, I'm not sure that it's in your text, but I'll show it to you here in case you encounter it in your future. The odds of that are pretty small, I recognize, is let's see, make sure I'm getting the structure right. AIBN stands for aza-isobutyryl nitrile, which you don't want to know, and that's fine. But one of the things to pay attention to is the fact that AIBN has an embedded nitrogen gas. Okay, so that's N2. Very stable. 70% of our atmosphere is nitrogen. We're swimming around in it, and very little happens to it. And if you add, again, light or heat, you can actually break these individual nitrogen carbon bonds to create a new, more stable nitrogen-nitrogen pi bond. That's a gas, and this is irreversible. Once you make nitrogen, there's not any going back, and you end up with two of these T-butyl radicals, which then you can use in chemistry. All right. Couple of things now about radical reactions. They tend to happen as chain reactions. And this is mechanistically sometimes uncomfortable because we're used to drawing mechanisms where there is a starting material and a product and one or a few steps going from starting material to product. Radical chain reaction mechanisms are a little bit different. They go in phases. You have an initiation phase where you generate a radical. You have a propagation phase where there's a couple of steps that take one radical and convert it to another, and as part of that process, you're spinning off product all the time. And then at some point, you have a termination phase, and the thing is that the initiation and termination phases are relatively rare, but once you get the reaction going, it's the propagation phase that's the one that takes up most of your reactive material. So let me give you an example of that. We'll deal with specific reactions later. I want to introduce these mechanistic steps and then show you a couple of places in your everyday life where you encounter this kind of thing. So radical chain reaction mechanisms. I've talked about radical initiators. Initiation means going from 0 radicals to radicals, 1 or 2. So as an example of an initiation step, let's use light to convert bromine into 2 radicals. Propagation step. And I guess I should say overall what I'm going to show you here is conversion of methane using bromine under radical conditions to bromomethane. And we'll have HBr as a byproduct that we won't really care about. Okay, propagation steps. So in this step, one bromine radical finds a methane molecule. I should point out that radicals are reactive, and so it's relatively rare for one radical to find another. That is, at the early stages of the reaction, one radical is going to be surrounded by a bunch of stuff that is not a radical, and so a propagation step is far more common than what we could call a termination step. And I'll skip ahead to what a termination step looks like. You might say, well, can't those 2 bromine radicals recombine immediately to give me just back to bromine? And the answer is yes, and that happens all the time. Okay? But suppose bromine is near a molecule of methane, what can happen is the bromine radical can literally strip a hydrogen atom off of methane. This mechanistic step is called hydrogen abstraction. And I've not really found it useful to think about HOMO and LUMO here. Often we've dealt with breaking bonds before as let's dump 2 electrons into an antibonding orbital and then we make a bond and we break a bond. It's not that useful to think of it that way with radical steps. So what's going on here is basically bromine with its 1 electron is taking hydrogen with another electron to create a new bromine hydrogen bond and leaving behind a methyl radical. So the reason this is called a propagation step is because you started with a radical and you end up with a different radical. But there's no radicals consumed, just trading, okay? A second propagation step might be to take methyl radical and have it encounter Br2. Here the methyl radical is stripping a bromine atom off of Br2 to create a new carbon-bromine bond, and byproduct of that is a new radical. So we have this radical and we're trading it for that radical. That's a propagation step, but if you've looked at what we get out of this reaction, this is our product. So the confusing thing about radical mechanisms is the mechanism isn't done when you generate product. Product is cranking out all the time, but as soon as we make Br radical, we go back to propagation step, we'll call it A. And then we go again. So it's a cycle, a chain that keeps cranking and spitting off product all the time. Now, termination. What, aside from bromine reacting with itself, you can think of a number of different termination steps. This is, again, a confusing and uncomfortable thing because there's a potential lot of things going on. So termination step involves 2 radicals finding each other. So Br could find another Br to create bromine. Br radical could find a methyl radical to create another molecule of methyl bromide. And it turns out that 2 methyl radicals could also find each other to make ethane. The thing that, so you might ask, well, how do you've got all of these things going on. Aren't these, this is unreacted starting material, which is fine. We can use that in propagation step 2b. This is product, which is great, but what about ethane? We don't want that forming. And the answer is that initiation steps, like termination steps, are relatively rare. It's hard to generate radicals. Most of the time they would just you make the radical from your initiator. Most of the time it recombines back to here. Occasionally one radical finds a non-radical nearby and you start a chain reaction, and that just goes and goes and goes and cycles through. Termination steps where radicals find each other are also rare. So basically all we need to worry about is the fact that we get product coming out of this cycle from A to B and then from B back to A. Okay. All right. I guess the arrows really aren't helping there, so I'm going to get rid of them. Questions so far? Lots of questions. Good. So I will begin on the left and move to the right. My left, not yours. Yes?
I guess, why wouldn't it stop, for example, at the radical method? Like, is it just due to stability of the...
Yeah, so why don't we just stop here? Methyl radical is unstable. You can't bottle it. It will react with something.
Is that just kind of experimentally derived, or is that Explain that with electronegativity or.
Can you rationalize that you can rationalize that probably based on CH bond strength. CH bonds are quite strong, and so to get rid of them is way uphill in energy, which means the radical itself is pretty unstable. Okay, yeah.
During the propagation step, do you end up with the same amount of product that you put in, or is it actually being propagated maybe?
Do you end up with the same amount of product? Ultimately, you're limited by however much starting material you put in. Yeah, so let's think of it this way. You can almost think of the radical, I mean, it's not this, but suppose you have 1 mole of methane. At any given time, you're going to have way less than 1 mole of bromo radical or methyl radical going. But the fact that that reaction cranks through both those steps means the reaction itself, even though there's way less than 1 mole of radical present, you can crank through tons of material that way. It's almost as though the chain reaction is a catalyst. It's not exactly that way. That maybe didn't answer your question. Try again.
Is it self-sustaining in the fact that it gives product and the product is immediately used up again, or is it actually producing more product every cycle?
So is the reaction self-sustaining until you run out of starting material? Yes. Does this product go on to react? Can it? Depending on the situation, yes. For our purposes and dealing with bromine, no. We'll only worry about adding 1 bromine here. Do you get more methyl bromide than you have methane to put in? No, you can't. Yeah?
Are there things you can do to force termination?
Can you force termination? The more radicals you have, the more termination events can happen. You can also add things called radical scavengers, which are designed to react with and intercept radicals, and that can slow things down. Yes?
So is that one of the reasons, well, not that, the fact that, going back to AIBN, the fact that it can't go backwards, can't reverse, is that one of the reasons it's such a preferred initiator?
Yeah, the AIBN's a great initiator because once it goes, you end up with these 2 radicals, and these could totally recombine with each other. I mean, one of the byproducts is this beauty, and that happens. But the idea is that unlike bromine, which has the chance to recombine directly, AIBN sort of explodes nitrogen out of things, and then you've got these 2 radicals on either side that have, I think, a better chance of finding other stuff. All right, yeah.
So how come the methyl radical can't attack other metals? It only attacks like bromine bonds?
Great. How come the methyl radical can't attack other methane? So actually, what you were proposing is in fact going on too, but it is silent, meaning undetectable. You can't tell that it happened because all it would do is trade 1 methyl radical for another. Similarly, we might draw another silent propagation step in which a bromo radical might react with Br2, molecular bromine, to make this and that. Again, silent, you can't tell that it's going on. Certainly it is. It just doesn't lead to any difference in the situation. Yeah?
So with the bromine methane reaction, are the products more stable than the reactants, or like are they about the same amount of stability, so that's why it happens, or like?
Right, so to do that, we would simply need to look up bond strengths. So do I have these values in front of me? Maybe. Common functional groups, new. There used to be a table at the back of the book about bond strength, but I think they got rid of it because they realized no one cares. I care. I don't know. It's probably a couple years old. Bond dissociation energies. Here we go. All right, so I'm going to write down strengths of bonds that we formed versus bonds broken. The BR-BR bond is worth 46 kilocalories per mole. The CH bond in methane is worth 104. Let's see, the HBr bond is worth 88. And the CBr bond is worth 70. So it comes out just, let's see, 150 here and 158 here. So bonds formed versus bonds broken, it's just a little bit downhill in energy. Yeah. Cool. All right, what else? Okay, let's see. Yes?
Would this be considered a fast reaction, like rather than like a fast reaction, like a slower reaction?
Is it fast? I think so. I actually don't run radical reactions. Well, actually, you do run a radical reaction anytime you start a fire. We're going to talk about that. Radical species are generally not very long-lived, so yeah, I would say probably pretty fast. All right. So just for some perspective, what we've done here in describing reacting Br2 with methane is we've done a holy grail thing in chemistry. That is, we took something that had only CH bonds and that was basically useless to us except we could burn it. And now we've put a good leaving group on there and we can do all kinds of chemistry, all right? This type of reaction falls into a class of reactions called CH activation. You're replacing a CH bond with something else that's more useful. That is the way you take petroleum feedstocks and turn them into useful commodity chemicals. And organic chemists are always in search of better CH activation reactions. By the way, even though this works on paper, it's not useful enough that everybody does it in the lab. There's still a need for a lot better CH activation reactions. But this is now going to facilitate a lot of things for synthesis. As an example, I once put on an exam this kind of question where I said, okay, fine, make this from that. You got to start from something that's just a hydrocarbon. No leaving group, no nothing. And the idea is you needed to use a radical reaction to first do CH activation. We'll talk later about how you can do this and only get the bromo at the tertiary carbon. But once you've got it there, you can do all kinds of, for example, elimination chemistry, followed by hydroboration, oxidation to get the OH on the less substituted carbon. And then you just need to do some converting the OH into a good leaving group and doing some substitution chemistry. So stay tuned. We'll maybe talk about that in a little bit more detail later. But this is useful in the sense that now you can use starting materials that aren't even alkyl halides. All right. So let's talk about fire and then plastic, if we have time. It turns out combustion is probably the radical reaction that humans are most familiar with. It's the one that we've been using for the longest amount of time. Combustion is deceptively simple. So let's just show the balanced reaction. Oh, hate balanced reactions. For methane combustion. You take methane and oxygen and you generate CO2 and water. I think we need a couple of those and a couple of those. Looks good, right? Deceptively simple. I say deceptively simple because there's probably, people have studied combustion and the various things that are going on in the flame. And there's maybe 300 plus, 350 plus things going on all the time in that flame if you include if you include the potential involvement of nitrogen. So combustion, if you look at the mechanism, it's very complicated. And it's still, people are still publishing papers about it. So even though it's easy to burn stuff, it's somewhat difficult to understand what's going on while you burn the things. Let me give you just a few examples of the reactions that are going on. First, consider the radicals that are going to be involved in this mechanism. Combustion requires oxygen. You have learned to draw oxygen as this lovely Lewis structure that actually doesn't capture very much about oxygen's reactivity. If you do the molecular orbital picture of oxygen, you come to the conclusion that oxygen is actually a diradical. And a better Lewis structure that indicates that diradical, a better resonance structure might be this one. Even this one is incomplete, but I guess we could say those two are resonance structures. I don't know. But you've got basically a radical, single radical on either of those two oxygens. That radical can exist in a couple of different states. One, in the singlet state, the two individual radicals are aligned anti-parallel to each other. That is, one has upspin, the other has downspin. That's actually less stable and more reactive. You don't need to know about why, though if you really want to know, you can come take my Chemistry 552 class. Actually, I don't think I'm teaching that in the fall, so you can take that from, I think, Dan S., who's teaching it. Or it can exist in the triplet radical state, which is you have parallel spins. The triplet is a little bit more stable. Most of the oxygen around us is in the triplet state. In order to get combustion to happen, you got to switch oxygen from the triplet state to the singlet state. That requires energy and takes a little bit of time, for which we're all grateful because we are not on fire. All right, so oxygen in its singlet state is one of the important species that's involved in combustion. You'll also see various other oxygen-centered radicals. For example, this is the hydroperoxy radical. This is the hydroxy radical. You'll also encounter just a hydrogen atom as a radical, to say nothing of the carbon-centered radicals that are generated during the process. So I'm going to show you a series of reactions. There's like 9 of them involving radicals that can take you from methane to CO2. But understand, this is just a small portion of what's going on. A lot of these reactions are highly exothermic. They release a lot of heat, and that can cause, we'll actually talk about where the light from fire comes from too, but hang in there with me. All right, so let's start with, all right, let's see. This is not the whole, set of reactions that are involved in combustion, but these are enough to get you from methane to CO2. So singlet oxygen, 2 radicals, methane. Hydrogen abstraction is one step. You have oxygen remove a hydrogen atom from methane. that generates a hydroperoxy radical, because oxygen was a diradical to begin with, and it generates a methyl radical. A next step would be to recombine that methyl radical with the hydroperoxy radical to make a new sigma bond. Oops. To generate methyl peroxide. For those of you playing along at home, that is a termination step in the sense that you recombine two radicals. But there's a lot going on in fire, and so there's a lot more radicals still present to do other chemistry. So one of the things that can happen to this methane, to this methyl hydroperoxide, I guess I should say at this point, I'm hearing some whispering out there, by which I infer that some of you are like, do we have to know this for the test? Yes. You do. Do we have to memorize all of it? Yes. You do. Do I care? No. Do not. I'm not into memorizing things, as you can see. I'm into using principles you already understand to apply in new and unfamiliar situations. I want you to have a feel for what's going on with the radicals when you light candles on birthday cakes and other things. By the way, shouldn't we just all stop as a society blowing on birthday cakes in the aftermath of COVID? Like, isn't that something that should just die? No? Nice and moist. Ew, that's disgusting. Okay, so once you have this methanol, basically methanol or methoxy radical, you can do another interesting oxidation step where you make a new pi bond here, and then the hydrogen goes to make a new water molecule with a peroxy radical. That will take you to formaldehyde and water. By the way, if you're watching along, we've made a couple of water molecules, and that's where the water comes from in combustion. And then there's some other things that can happen, because I want to show you how CO2 happens, not because I want you to memorize everything. We'll take formaldehyde, and then you can use a hydroxy radical to remove or do hydrogen abstraction to generate this weird radical and water. At that stage, depending on the mix of oxygen and fuel, you can take that basically formaldehyde radical and you can react it with another hydroxy radical, and that will generate CO, or carbon monoxide, which you can draw as this resonance structure as well. That's a product of incomplete combustion. Instead, if you continue onward, you can couple the hydroxy radical with the formaldehyde radical to make formic acid. Starting to see now we've got two oxygens attached to carbon. You can then take formic acid and have another hydroxy radical remove a hydrogen atom, and then finally this is where we'll generate CO2. You can sort of have a fragmentation process happen where you lose a hydrogen atom, you generate CO2, and you make, in this case, H2, which you can go on to react in other ways. So that's just a brief summary of the kinds of things that are going on. Radical chemistry is really difficult to predict. Some of you who are used to well, if I just master the fundamental principles, then I should be able to predict everything. We're not quite there with combustion. People understand it pretty well and are able to use it, but even still, there's papers coming out in journals still about what's actually going on and doing calculations to try to determine what the best pathway is. And if you've got hundreds of these things going on at once, this is basically a mass of differential equations that is difficult to handle. And if you're a chemical engineer, that just may sound very exciting to you, so I encourage you to do that. Keep on. And anyway, so those are examples of the reactions that generate CO2 from methane. Now, what's going on in terms of the release of light? So all of these reactions, many of them are exothermic. They generate a lot of heat. And there are a few things that are responsible for light in flame. So let's just talk about a few of them. Let's see what time it is. Right, so there are a couple of things that, in addition to all of this, as part of combustion, you can actually recombine some of the methyl radicals to generate larger species. And the more, if you start generating larger carbon species, you generate what's called soot. So any of the dark smoky stuff that you can hold, like hold metal or a spoon over the flame, and you start to see condensation of this dark soot on the thing you're holding over the flame. What that is that's recombined radicals to form larger hydrocarbons. There's a few intermediates that aren't on this list that are nonetheless important in fire. One of them is called the methylidine radical, which just looks insane. And then another is C2, or diatomic carbon. These are both formed as intermediates, and we don't need to worry about the radical mechanism that generates them. But basically, both of these have electronic transitions that can be excited by the heat that's present in the flame, and they get electronically excited, and then relaxation accompanied by release of a photon allows them to get back to the ground state. And in general, that photon is in the blue part of the spectrum. So if you've ever seen a Bunsen burner that's tuned so that it's got enough oxygen going through it, such that combustion is really rapid and you don't have a lot of soot present, what you're seeing in terms of the flame is these two molecules being excited and relaxing and releasing photons. How about the sort of bright yellow color? So in fire, the yellow comes from, you could call it incandescence or black body radiation of soot. So black body radiation happens as particles get very hot and vibration of atoms along the surface of the particle releases light. The hotter something is, the brighter it glows, and there's a whole thing there. But what you're seeing in terms of like a regular candle that sort of has this yellow flame, you're seeing soot particles there that are just hot and glowing, in the same way that if you turn on your oven element and turn it up high, it starts to glow red, and if you turn it up even hotter, it would start to glow brighter than that. So what you're seeing in terms of the flame is either light released because of electronic transitions among these radicals, or you're seeing just sort of regular, boring, old hot stuff glows. Yeah?
Why does the light stay contained, like we call it fire?
Why does the light stay contained in the fire? That's a good question. What you're seeing there is a couple of things. You're seeing convection and gravity, and then temperature falling off. So it would be light, the flame would be bigger if it didn't cool off so much as it went away from the source of the flame. Yeah?
So a clean burning fire would be a blue fire? And then
Clean burning fire means there's not a lot of soot, meaning combustion's basically complete. You're generating mostly CO. Whoa, that's fun. Mostly CO2 and heat, and so yeah, mostly you won't see incandescence because you haven't got a lot of soot. Okay, what else? All right, I'm afraid there's chemical engineers here that are like, come on, man, we totally know what's going on here, and you just totally destroyed it. So, anybody wish to correct or add to? Yeah.
Okay, so 3 up from the bottom in those steps.
Let's just be clear, Hunter. Is this a correction or a question?
Good, it's a question.
Oh, okay. All right. Really. I mean, you raised your hand pretty quick after that, so we're all like, "Oh, this guy knows." Okay.
So I'm sorry. 4 up, you have a radical reacting with the H bond instead of the
Right.
Why is that?
I don't know, other than these are 2 options. It's like the analogy, I guess, would be we've seen in cases where the same nucleophile / base can do either substitution or elimination chemistry. There's just 2 different options here. I don't know which one's more favorable. They certainly would have different energetics. One would be maybe more favorable than the other, and I don't know. Kinetically, what they say is that if the combustion isn't complete, if you don't have enough, I think, oxygen for the fuel that you've got, you tend to make carbon monoxide. Don't know why. Yep. Others? Well, we didn't quite get to plastics yet, but what I want you to do over the weekend is I want you to pay attention to the plastic products that you use and take a look at the bottom or wherever and see what the little symbol is on there. Whether it's 4 or 2 or 1, look for things like PE or HDPE. We'll talk about what all of those things are when we talk about radical polymerization and then plastic structure. All right, see you next time.